Hello, this is Dr. Hanaa Assil, and this is Unit 5 of the Pearson Edexcel International A-Level. This was the paper in January 2022. So the first question says, this question is about transition metal complexes. The bonding within the complex shown is what? So if we draw this complex, it's between copper 2+, 4 ammonia molecules and 2 water molecules. You should realize that each of the water molecules has covalent bonds within it. So the H2O, each of these H2O has covalent bonds. Each of the ammonia has covalent bonds. And between these molecules and copper, there is what we call dative or coordinate bonds. So the bonding in the complex is both covalent and dative bond. Which complex is tetrahedral? Remember that. Different complexes, you should be familiar with their shapes. Now, if something is bonded to 4 molecules or atoms like this platinum molecules, which can be cis or trans, and remember that this is important to us because the cis form acts as an anti-cancer drug. But this is a complex between platinum and 4 other molecules or ions, and you should remember that this platinum molecules are planar. So this is actually a square planar structure. Now, when copper bonds with 4 water and 2 OHs, that means we have a total of what we call 6 ligands complex to it. When you have 6 ligands complex to it, this structure is octahedral. The one in C also has 4 ammonia and 2 water, so also the copper is complex to 4 molecules of ammonia and 2 molecules of water. That's an octahedral structure. But when cobalt is bonded to chlorine or chloride ions, these are tetrahedral, and the reason that they are tetrahedral is that the chloride ions are large ions, so they take more space, so they need to be arranged in a tetrahedral structure for minimum repulsion between the bonding pairs of electrons. So this is the one that is tetrahedral. Which complex contains a bidentate ligand? Remember, a bidentate ligand is one that attaches with 2 coordinate bonds to the central ion. So if we look at the one in A, this is the structure that is complex to cobalt in A. This actually has 3 nitrogen atoms. You know that each nitrogen atom has a lone pair of electrons that can be used to bond to the central atom in a coordinate bond or a dative bond. So this is called a tridentate ligand. It forms 3 dative bonds to the central atom. What about these? These are ammonia and water. Each of them is a monodentate ligand. Each of them has only 1 lone pair of electrons that makes 1 dative bond to the central ion. So these are monodentate, each one of them. So ammonia is a monodentate ligand, water is a monodentate ligand. Now this one that is bonded to nickel, this is something that has 2 nitrogen atoms per ligand, and that means that each of the nitrogen atoms has a lone pair of electrons that can form a dative bond to the nickel, and that means each of them forms 2 dative bonds. This is a bidentate ligand. The EDTA, this is the structure of EDTA. You should realize that EDTA can form 6 coordinate bonds to the central metal ion. It has 2 nitrogens and it has O negatives that can bond to the central ion. So we say this is a hexadentate ligand. So what is he asking about? Which one is bidentate? So the one in C is the one that is a bidentate ligand. A hydrogen-oxygen fuel cell is used to provide electrical energy for an electric motor in a car. The electrolyte in the fuel cell here is acidic. I'm going to remind you that the hydrogen-oxygen fuel cell can either be alkaline, so in that case, these are the equations that happen if we have an alkaline medium, and it could be acidic, so these are the equations that could occur if we have an acidic medium in the fuel cell. So which one is he talking about? He's talking about that's the one that is acidic. What is the half equation at the anode? So the one at the anode is where the hydrogen gas changes into or loses 2 electrons and becomes 2H plus ions. Hydrogen-oxygen fuel cells have advantages over methanol-oxygen fuel cells in vehicles. Which of these is an advantage of the hydrogen-oxygen fuel cell? Remember that the main advantage of a hydrogen-oxygen fuel cell is the fact that its final product is only water. So the only thing that is given out in these fuel cells is water or water vapor. So there are no pollutions. Something like methanol would give carbon dioxide, which causes climate change, while the hydrogen-oxygen fuel cell, the emissions do not contribute to climate change. An electrochemical cell is made from the electrode systems shown by these half equations. So he has the one for Ag plus gaining electron becoming Ag, and VO2 plus 1 plus 2H plus electron to give this product. Now, the apparatus used to measure the value for E cell under standard conditions is shown. So he has a half cell that has 1 mole per decimeter cubed of silver ions with silver electrode, and then the other electrolytes in the other half cell with a platinum electrode. And the first question is, which silver compound could be used as the electrolyte in the left-hand half cell? Remember, if we put silver in a silver electrolyte solution, this should be a solution. So it should be made of something that is soluble. So the question is, which of these is soluble in water and would form an aqueous solution? You should know that all nitrates are soluble and form aqueous solutions. So this solution should be silver nitrate, not any of the others, because the others are insoluble in water. The electrolyte in the right-hand half cell is prepared using equal volumes of what? I'm going to remind you that the electrolytes in these cells have to be concentration 1 mole per decimeter cubed. But if you have 2 solutions, then you have 2 mole per decimeter cubed, because if you're going to add them together, then the total volume is 2 decimeter cubed. So each of them should be 2 mole per decimeter cubed in order to have a total concentration of 1 mole in 1 decimeter cube. So if I have 2 mole per decimeter cubed of the first one with 2 moles per decimeter cubed of the second one, these are mixed together, so that makes each of them 2 mole in 2 decimeter cubed, so the concentration is 1 mole per decimeter cubed. Which is the equation for the overall cell reaction under standard conditions? Okay, what do we have? These are the equations he gave me, and these are the ones that you can get from the data book. But remember that one of them has to be oxidation and the other has to be reduction. Now, we're going to decide which one of these is going to lose the electrons and which one is going to gain. Remember, if you look at the E note for each one, the one that has a more positive E note is the one that is more easily reduced. It is the one that gains electrons. So which of these is more positive? It's the second equation that has an E of +1. So that means that actually this is the one that will gain electrons. So we're going to leave it as it is. But the other one has to lose electrons. And when we invert the equation, we have to invert the sign. So instead of having this is what we had. Silver plus electron to give silver, and the E note was plus 0.8. Now this is the one that is going to lose electrons, and its E will be minus 0.8. Now we can add them together in order to get the overall cell reaction. How do we add these two half equations? We cancel the electrons on both sides of the arrow, and we add up whatever is before the arrow to give whatever is after the arrow. So this is the final overall cell reaction. Which is the value of the E cell for this reaction? Now we're going to look at the E note for each of these. The E cell is the E reduction plus E oxidation. So the total of these E's is the E cell, so that is plus 0.2. Which is the cell diagram for this cell using conventional representation? Okay, what do we have? We have the Ag is the one that lost electrons, so this is the one that we write first in the conventional representation of half cells. The one that lost the electrons goes from silver solid to silver plus aqueous, so that is what we start with. And then we're going to have a salt bridge, so the double lines after that are representing the salt bridge. And then I'm going to have the other one in the other half cell. So what did we have? We have these equations, the VO2 plus 2H plus, changing to VO2 positives plus water liquid. And remember, when the electrolyte has two solutions, like these vanadium compounds, then the electrode has to be a platinum electrode. So B is our correct conventional representation of the half. Then the next question says a mass of 4.179 grams of hydrated iron 3 sulfate was dissolved in deionized water, and the solution made up to 200 centimeter cube. What is the concentration of sulfate ions in the solution? Okay, you should realize that if I start with hydrated iron 3 sulfate, when it ionizes, it's going to give 2 moles of iron 3 plus and 3 moles of sulfate ion. So if we have the number of moles of the hydrated salt, the number of moles of the sulfate ions is 3 times that. So let's get number of moles of hydrated salt, mass over the molecular mass that he gives me. This is 0.01 mole. But that means that the number of moles of sulfate is 3 times that, so that is 0.03 mole. Now what does he want? Concentration. Concentration is number of moles over volume. So that number of moles over the volume in decimeter cubed. So that means I divided the 200 by 1,000, and this gives me the concentration of the sulfate ions. Question 5 says the infrared spectrum of a compound X is shown. What could be compound X? Well, we look at the main peaks that we see in this IR spectrum. You should realize that that wide peak around 3,000 is for the OH group. The peak at around 1,700 is for a carbonyl group. That means I need both of these in my structure, so that would be A. The others are either aldehyde or alcohol or ketone, so they don't have one of these peaks. So C will not have the peak for OH, B will not have the peak for C double bond O, and D will not have the peak for OH. So the only one that has both peaks is A. Question 6 says methyl benzene reacts with a mixture of concentrated nitric acid and concentrated sulfuric acid to form 2,4,6 trinitromethyl benzene. What is the number of peaks in the carbon-13 NMR of methyl benzene? Let's take a look. How many different carbon environments? And remember, he's talking about methyl benzene, the reactant, not the product. So we have one at the CH3 branch. We have another one at the carbon on the benzene to which the CH3 is attached. And then the other carbons are symmetrical. So we have a total of 5 different types of carbons or different carbon environments. What type of reaction takes place? This was the equation he was talking about. What type of reaction is this? Remember that benzene ring, when you reacted, for example, with the nitro group, then we have what we call electrophilic substitution. The benzene ring donates electrons to the N plus of the NO2 minus ion, and then the electrons holding the hydrogen are donated to the benzene ring. So this is electrophilic substitution reaction. Which expression shows the mass in grams of 2,4,6 trinitromethylbenzene formed from 10 grams of methyl benzene if the yield is 85%. So this was the equation. He started with methyl benzene and he's saying he has 10 grams and he's asking for the mass of the product. So of course, the first thing we get is the number of moles of the methyl benzene. And then we determine the mass. This will be the same as the number of moles of the product. 1 mole gives 1 mole. So that is the same as number of moles of the product. And then the mass of the product will be that times its MR. So he's not looking for the final answer. He's just looking for what are we going to do. So this is our answer. The mass spectrum of the compound shown is obtained using a high-resolution mass spectrometer. What is the M over Z of the molecular ion of this compound? So basically, he's asking what is the MR of this compound. So we look at how many carbons, how many hydrogens. So this is what the structure is. And that means that the formula is C6H4O. Then I can use these values that he gives me to calculate the MR. And that comes out to be this number. Okay? A group of students carry out an experiment to find the concentration of chlorine in a solution. Excess potassium iodide is added to a 10 centimeter cubed sample of the solution. The iodine produced is titrated with a solution of thiosulfate ions of known concentration using starch indicator. The concentration of the chlorine was between 0.038 and 0.042. So the first question is, what concentration of thiosulfate is required to give a titer of approximately 20 centimeter cube? So he's telling me that the original concentration of chlorine is about 0.04. And we need a titration of the thiosulfate. We need a titer of 20 centimeter cubed of the thiosulfate. So what would be the concentration of the thiosulfate? Well, let's take a look. Number of moles of the chlorine is concentration times volume. And this is the same as the number of moles of iodine. Then the number of moles of thiosulfate from the second equation, the thiosulfate is twice the number of moles of iodine. And then he wants what? He wants concentration. Concentration of the thiosulfate is number of moles over the volume. He's telling me he wants a volume of 20 centimeter cubed, so that's 0.02 decimeter cubed. And that means I need a thiosulfate of concentration 0.04. What is the most suitable volume of potassium iodide solution that we need to add to 10 centimeter cubed of chlorine solution? Okay, so he's asking for volume of potassium iodide. We got that the number of moles of chlorine is this. And from the equation, the iodide should be twice the number of moles. So the number of moles of iodide is twice of that. And that means that the volume that I need exactly should be about 8 centimeter cubed. But that's not our answer, because he wants to add excess potassium iodide. So the minimum I can put is 8, so excess would be the 10 centimeter cubed of potassium iodide. Please pay attention to the details of the question. What is the color change at the end point of the titration? Remember, what were we using as indicator? We were using starch. I started with iodine, and then the iodine produced is titrated with a solution of thiosulfate using starch indicator. So if we start with iodine and then it changes to iodide, remember that the iodine with the starch makes a dark blue-black color. Now at the end, the iodine is used up, so at the end there is just starch solution with iodide that is a colorless solution. So in these cases, when we're trying to titrate thiosulfate with iodine using a starch indicator, the iodine with starch at the beginning is blue-black, and then at the end point, when the iodine is all used up, it turns color. The formula of 4 ions are shown. How many of these ions contain a metal with an oxidation number of +3? You should know how to calculate oxidation numbers. Remember that each ion, for example, let's take the chromate ion at the beginning. This has an overall charge of -2. And you should know that each oxygen has -2. I have 4 of them, so that's -8. So in order to have an overall charge of -2, the chromium is +6. Are you familiar with this calculation? Let's try again. Aluminium O2 minus, the overall is -1. Each of the oxygens is -2, so the aluminium has to be +3. FeCN6, you should realize that the overall charge is -4, and each cyanide ion has a -1. So that means that my iron has to be +2. The last one, chromium with chlorine and water. Remember that here the overall is +1, and each of the chlorines is -1, or each of the chlorides is -1. Water has no charge on it. So it's the charge of the chromium plus 2 times -1 for the chloride. Overall should be +1, and that means the chromium is +3. So he's asking how many of these ions contain a metal with oxidation number +3. That's aluminium and chromium, so that is. Then in section B, he says this question is about silver and silver compounds. Glass decorations are made reflective by coating their inner surface with silver. This is achieved by using the reaction between silver nitrate solution, ammonia, and glucose under alkaline conditions. Initially, the colorless complex ion diamine silver forms explain the shape of the silver ammonia complex. Okay, this is silver with two NH3s complex to it. So this is the shape of the complex. This is a linear shape with bond angle 180. Of course, this is because we have two bonding pairs of electrons, so they have to be linear for minimum repulsion between the bonding pairs of electrons. Explain why this silver ammonia complex is colorless. Remember, we said most of the complexes of transition metals are colored, but silver plus ions are colorless. This is because silver, first of all, electron configuration of silver, this is something that has atomic number 47, so it ends with 5s1, 4d10. And that means if it does +1 ion, where are we going to remove the electron? Remember that in transition metals, we remove the electrons from the 5s first before the 4d. So to form an Ag+, I have this with a complete 4d sublevel, and that means if I have the ion with complete D sublevel, they do not have a color. Do you remember why complexes of transition metals originally have colors? Remember that if we have a complete 4D, then no color. But if we have incomplete 4D, so the complex will have a color and they will absorb in the visible spectrum. Why is that? Remember that these 5D orbitals are originally the same energy, so we call them degenerate. Now, when two of the d orbitals are repelled by bonding electrons with the ligand, they split so that two of the d orbitals are at a slightly higher energy than the other three. So when light shines on the solution, if we have incomplete d orbitals, then an electron absorbs an amount of energy equal to the difference between the orbitals, and the electron jumps to the higher energy level. The rest of the visible spectrum that is transmitted through the solution is the color observed. So long as the d orbitals are incomplete, then an electron can absorb energy, move to the higher d orbitals, and that causes a color. But why is it that the silver complex is not colored? That is because all the 4d orbitals are complete, so there is no transition of electrons between the d orbitals, so no energy is absorbed and there is no color seen for this solution. The diamine silver complex then reacts with glucose, forming silver and an organic compound 1. Complete the equation for the reaction. Remember that glucose is an aldehyde, and we said one of the tests for aldehydes is formation of silver mirror when we use Tollens reagent. So the silver ammonia complex is the Tollens reagent, and this gives a silver mirror plus what? What is left is ammonia and water. And then we need to balance. So we have 2 nitrogens before the arrow. I need 2 nitrogens after the arrow. And then how many oxygens before the arrow? I have 1, 2, 3, 4, 5, 6 in glucose plus 1 of the OH minus, so that's 7 oxygens before the arrow. After the arrow, I have 7 in compound Y and 1 in the water. So I need to increase the one before the arrow, but that means that I will need to put a 2 in front of the silver complex in order to balance the charges. So if I have 2 OH minus, I must have 2 pluses in the complex. And that means now I have 2 silver, so I need 2 silver. And how many nitrogens do I have now? I have 4 nitrogens. And if you count the hydrogens now, they will be balanced. So that is the balanced equation. Draw the structure of Y. What is the structure of Y? You should realize that when you have an aldehyde and you add Tollens reagent is an oxidizing agent. So it will oxidize the aldehyde to acid. So this would be the structure of Y. The overall reaction in a silver cell used in watch batteries is this. The half equation for the reaction at the positive electrode is this. Deduce the half equation for the reaction at the negative. Of course, if we have the overall equation and this is 1/2 of it, then the other one would be the other half. So I have already used up the silver oxide and the water, so I will need the zinc going to zinc hydroxide, and that means zinc with the hydroxide ions will give zinc hydroxide. And of course, when the zinc changes to zinc 2 plus, that means it gave 2 electrons, or it lost 2 electrons. So this is the half equation at the negative electron. This compound is an amine, and it is used in the treatment of hay fever. Deduce the classification of the labeled amine group. Okay, what do we mean by classification of an amine group? Remember that amines can either be classified as primary or secondary or tertiary, depending on how many substituents we have on the nitrogen of the amine. So if I have 2 hydrogens, and that means I have only 1 methyl group attached to the end, then this is a primary amine. If I have 2 alkyl groups, you know that an alkyl group is a hydrocarbon chain. So 2 alkyl groups, that means I have substituted 2 of the hydrogens with carbons, then that is a secondary amine group. If I substituted all the hydrogens with alkyl groups, then this is a tertiary amine. So which type is this? This one has 3 alkyl groups attached to the nitrogen. So this is a tertiary amine. The compound pyridine is used in the synthesis of this compound. Like many amines, pyridine is miscible with water and the solution is alkaline. So explain each of these properties. Okay, why is it miscible with water? First of all, nitrogen has a lone pair of electrons, and this lone pair of electrons allows it to form hydrogen bonds with the water. So it will dissolve in water. Now, why is this solution alkaline? This is because this nitrogen group can accept an H plus ion, so it breaks up the water, it takes H plus ion, and it leaves OH minus in solution, causing it to be alkaline. A student suggested that the final step in the synthesis of this compound starts with the reaction between something that is an amine and chloromethane. Assuming the reaction is similar to that between ammonia and chloromethane, complete the mechanism for this proposed reaction. Some of the organic structures shown have been simplified. Include curly arrows and any relevant dipoles and lone pairs of electrons. Okay, so we have an amine. An amine has nitrogen with a lone pair of electrons, and it's going to attack the chloromethane because the carbon-chlorine bond The chlorine is electronegative, so it attracts the electrons, so the carbon is slightly positive and the chlorine is slightly negative. So these are the dipoles. Now when this attached to each, then the nitrogen is a positive center, so the electrons bonding the hydrogen will be donated to the positively charged nitrogen to give the final product. So we end up with this product plus the H and the Cl minus forming HCl. This question is about polymers. The diagram shows part of the structure of a polymer formed by condensation reaction between two amino acids. So the units here were amino acids. Predict the structures of the two monomers. Of course, when we're looking for the structure of the monomers, we look where is the linkage. This is an amide linkage, so it is linking one amino acid to the other amino acid, and that means that the part on the left is this kind of structure with an acid group. He's saying it's amino acid, so it's not an acyl group, for example, and the one on the right would have the amine group where it was attached. So when we join these together, the amine group joins to the acid of the other monomer. The diagram shows a repeat unit of an addition polymer. Now he's saying it is formed from two different monomers. Deduce the structure of the two monomers. Again, when it is addition, then each two of these was one of the monomers. So the two carbons on the left were originally an alkene of the structure, and the two carbons on the right were originally an alkene, so that when we do addition polymerization, they will give that product that was shown. Do we understand how to get the monomers? So in this case, when we have addition, we just take two carbons and we remove the single bond in the middle and change it into a double. A synthetic rubber polymer has this structure. The molar mass of the synthetic rubber is 300,000. So the polymer as a whole has an MR of 300,000. Calculate the approximate number of repeat units. So the one drawn up there is a repeat unit. What is the MR of this repeat unit? You count the number of carbons and the number of hydrogens, it comes out to be C12H14, and that means that the MR of each repeat unit is 158. But he says that the whole polymer has an MR of 300,000. So divide that by the 158. This gives me the number of repeat units in the polymer. Question 13 says the hydride of arsenic, which we call arsine, is a toxic gas used in production of semiconductors. Draw a dot and cross diagram for arsine. Okay, how do we draw dot and cross diagrams? We look for a S. Where is that? It is in group 5 or in group 15. So that means it has 5 electrons in its outermost shell. That means it needs 3. So it's going to share 3 of its 5 electrons with 3 hydrogens, and it is still left with 2 of them up there not taking part in the bonding. So this is the dot and cross diagram for ASH3. Arsine is a reducing agent and reacts with cerium 4 sulfate solution, forming arsenic. The data from an experiment are shown. So he has volume of arsine is, so this is a gas with a certain volume and pressure and temperature. And the volume of the cerium 4 solution is this. The concentration of the solution is this. And the first question says complete the half equation. So if we have ASH3 and I want it to change to AS, what am I left with? I'm left with 3H plus, and that means I have 3 electrons lost from that molecule. Okay, so this is the half equation for the reduction. Calculate the final oxidation state of the cerium ion formed in the reaction. How do I know the final oxidation number of the cerium ion? This is the information he gives me. So I can use it to get, first of all, the number of moles of the cerium 4 sulfate solution. So that's concentration times volume. Now I have the number of moles of cerium. Then the number of moles of arsine I can get from PV equals nRT. So the number of moles is PV over RT. Remember that in this ideal gas equation, the pressure has to be in Pascal. So that's okay. He gave it to me in Pascal. The volume has to be in meter cubed. He gives it to me in centimeter cubed. I have to multiply by 10 to the minus 6. Then R is a constant, 8.31 or 8.314, and the temperature has to be in Kelvin, so I add 273 plus 20, that is 293 Kelvin. This gives me a number of moles of arsine, and then I compare them. So the cerium has this number of moles, the arsine has this number of moles, and that means if I divide by the smallest, then the cerium is 3 to 1 to the arsine. And that means if I have this, the cerium is 3 to 1. That means I have 3 of the cerium taking the 3 electrons that were given by the ASH3. And that means that each cerium actually gained only 1 electron. And that means that my final oxidation number of cerium is plus 3. Did you notice this? Each ASH3 gives 3 electrons. And he's saying that the ratio of cerium to arsine is 3 to 1. So the 3 ceriums to 1 arsine, which gave 3 electrons. So 3 ceriums reacted with 3 electrons. That means each cerium 4 plus reacted with only 1 electron. So that means it went to cerium 3 plus or plus 3 oxidation state. Describe the reactions of separate samples of aqueous cobalt 2 sulfate with sodium hydroxide, ammonia, and HCl. Please note this type of questions about transition methods. So we're starting with cobalt 2. I want to react it with sodium hydroxide, ammonia, and HCl. For each reaction, link your description to an appropriate equation. State symbols are not required. So the cobalt 2 plus, when I dissolve it in water, it forms this kind of complex, and you should remember that cobalt in water forms a pink solution. Then he wants reaction with sodium hydroxide. When we add sodium hydroxide to the cobalt 2 sulfate, it forms this complex, which is a blue precipitate. Please remember, when you add sodium hydroxide to the cobalt water complex, this is a ligand exchange process where we exchange 2 of the water with 2 hydroxide ions. And that means this is ligand exchange or ligand substitution reaction. And what we get is a blue precipitate when we add sodium hydroxide to the cobalt solution. And then when we add ammonia, if we add ammonia to the cobalt water solution, this forms a yellowish brown solution or a yellow solution of the cobalt ammonia complex. So we're again replacing the 6 water ligands with 6 ammonia. So this is again a ligand substitution reaction. This forms the cobalt ammonia complex. It is a yellowish brown solution. When we add concentrated HCl, what we get now is a blue solution, and that is because the cobalt will form a complex with 4 of the chloride ions in a tetrahedral structure. This compound is a blue solution. Okay, please remember these colors and remember what happens with hydroxide, ammonia, and HCl. Question 15 says a compound Q contains the elements carbon, hydrogen, and oxygen only. Combustion analysis of 4.91 grams of Q produces 14.6 grams of carbon dioxide, 3.58 grams of water. Show that the molecular formula of Q is this. So when we have this kind of questions, we get the number of moles of carbon, number of moles of water. So let's get number of moles of carbon dioxide first. The carbon dioxide is mass over molecular mass. So this gives number of moles of carbon dioxide. You should realize that number of moles of carbon dioxide would be the same as number of moles of carbon because the carbon dioxide has one carbon. So the mass of the carbon is the number of moles times its MR, or its mass number. So this is the mass of carbon. We do the same for water, number of moles of water, but remember that water has 2 moles of hydrogen. So the mass of hydrogen would be the MR of hydrogen is 1 times twice the number of moles of water, because each mole of water has 2 moles of hydrogens. So this is the mass of hydrogen. Now we can get mass of oxygen because we started with 4.91 gram of Q. So the mass of oxygen is the rest of the 4.91. So this gives me the mass of oxygen. And then I can try to calculate the empirical formula. So the empirical formula here, we divide each of them with the molecular mass of each one, or atomic mass of each one. This gives me numbers. I then divide by the smallest to get the simplest ratio. So this gives C10H12O. Okay, please notice this kind of question. It's repeated in many exams. A high-resolution proton NMR spectrum of Q is shown. So this is proton NMR of Q. Deduce the structure of Q. Justify your answer by considering the relative peak areas. So this was the proton NMR. He says the relative peak area, the chemical shifts, and the splitting patterns, and refer to the data booklet. And he's telling me that the peak at 3.6 is due to proton environment on a carbon bonded to benzene ring. So this, we know that this is the formula. This is the formula that we just calculated, C10H12O. We know that the peak at 3.6 is due to a benzene ring. So I have a benzene ring attached to something. And then we look at the splitting patterns of the other peaks. So I have a peak at about 1 ppm. This is a triplet, and then another one at 2.4, which is a quartet. So usually, if we have a triplet next to a quartet, that means the triplet is due to CH3. And remember, he gives you area under the curve is the number of hydrogens. So I have a CH3 next to a CH2. So that the CH3 is a triplet and the CH2 has 3 hydrogens next to it. So that is a quartet. And then we have this data booklet. If we look at it, we will find that first of all, the ones at 1 is due to the CH3, CH2, so that's what we got. We also have the peak at 2 point something, so this is due to a hydrogen that is next to a carbonyl that has a neighboring carbonyl. So this is either an aldehyde or a ketone. And we have the one at 7 point something is for the benzene ring. So this is the deductions that we have so far. We have a benzene ring. We have the 5 hydrogens of the benzene ring. That's the one at 7 point something. The one at 3.6 is the one that has a branch on the benzene ring, and then we have a hydrogen next to a carbonyl, and that hydrogen has two carbons, or that carbon has two hydrogens, and it is next to a methyl group. So we need from all of these to determine the structure. So this is what we have. First of all, we have 4 proton environments, so 4 different types of hydrogens. The triplet next to a quartet means that I have a CH3 next to a CH2. The peak at 2.3, we said that means there is a carbonyl on the neighboring carbon. The peak at 3.6, this is a singlet, and that means there is no hydrogen on the neighboring carbon. So the branch that is attached to the benzene ring has no hydrogens on the neighboring carbon. And then the peak at 7.5, this is due to the hydrogens on the benzene ring, and it's a singlet, and that means that there is only one side chain on the benzene ring. It doesn't have more than one side chain. So what kind of structure can apply to all of this? So let's take a look at this. We have a carbonyl. On one side, we have a CH2 and a CH3. On the other side, we have a CH2, and that CH2 will be attached to the benzene ring. So that is the one at 3.6, and it's a singlet because there is no hydrogen on one side and there is no hydrogen on the other. So the CH2 is in the middle between the benzene ring and the carbonyl, and the benzene ring has only one substituent, and this would be the structure of my compound. Section C says benzoic acid is a white crystalline solid with the structure shown. It is found in many plants as it is an important building block for the biosynthesis of a variety of compounds such as plant hormones and attractants for pollinators. Usually we go through this list very quickly just to see if there will be anything that we will need. He says the role of benzoic acid in the chemical industry is widespread and approximately 500,000 tons are produced annually. It's used in the synthesis of many compounds. Such synthetic dyes are often classified as azo dyes. These dyes have a range of colors and wide range of uses in industries, including food and textiles. Their synthesis involves the formation of a diazonium ion. This ion then reacts with a phenol in a coupling reaction to form the dye. The relative simplicity of the reactions involved and the ready availability of starting materials make azo dyes cheap to produce. Salts of benzoic acid such as calcium benzoate and sodium benzoate are used in the food industry as preservatives. Now, where's the question? Devise a reaction scheme to produce benzoic acid from benzene. So we want to start with benzene and we want to end with benzoic acid. And he is specifying that I should go through bromobenzene and then Grignard reagent. Include the reagents, essential conditions, and give the name or structure of each of the intermediate compounds. Details of mechanisms are not required. So we want to start with benzene. We need to go through bromobenzene. So that means I need to put a bromine on my benzene. Remember that benzene plus bromine in presence of what? Of anhydrous iron 3 bromide as a catalyst. So this gives me the bromobenzene. And then he wants to go through a Grignard reagent. So how do we prepare a Grignard reagent? The bromo compound plus magnesium in dry ether. This will give me the Grignard reagent. And then the Grignard reagent is supposed to react with a carbonyl. Now, what kind of carbonyl? If I want benzoic acid, that means I need a carbonyl compound that has only one carbon. So actually, we could react it with methanol or carbon dioxide. So if I say methanol, then dilute HCl, it puts a carbon with an alcohol group on the benzene. And then I need the benzoic acid, so I need to acidify the alcohol using acidified potassium dichromate. That will end up giving me the benzoic acid. Benzoic acid can be used in synthesis of azo dyes. And he's saying I have this equation, so I have this with concentrated nitric in presence of concentrated sulfuric to put a nitro group on the benzoic acid. Draw the mechanism for this reaction using appropriate curly arrows. Include equations showing the role of the catalyst. So remember that I'm trying to put a nitro group on the benzene ring in presence of concentrated nitric and concentrated sulfuric as a catalyst. So first of all, how does the catalyst work? Remember that nitric acid with the sulfuric acid will give the NO2 plus that will react with the benzene ring plus the HSO4 minus plus water. This is because this is what actually happens, that the oxygen on the nitric acid will take up the hydrogen from the sulfuric acid, so this changes it into HSO4 minus, and then this results in the formation of the nitronium ion, the NO2 plus, that will react with the benzene ring. So how does this happen? We said this is an electrophilic substitution reaction in which the benzene ring donates electrons to the NO2 plus, and then the bond between the benzene and the hydrogen breaks up to put the NO2 on the benzene ring. So this is the mechanism for electrophilic substitution on the benzene ring. In step 2, the 3-nitrobenzoic acid reacts to form 3-amino. So he's changing the nitro to amino. How do we change NO2 to NH2? We add tin and concentrated HCl. He wants the reagents, tin and concentrated HCl. In step 3, the 3-amino benzoic acid reacts with sodium nitrite and dilute HCl, forming the diazonium ion. Now, state a temperature at which this reaction should take place, giving one reason for your answer. Remember, to form a diazonium ion, first of all, we react an amine with sodium nitrite and HCl. And we need to do this at a temperature below 10 degrees Celsius, otherwise the diazonium ion will break down. So temperature must be below 10 degrees Celsius to avoid decomposition of the diazonium ion to form other side products. Draw the structure of the azo dye formed when diazonium ion reacts with phenol. So he wants to react the diazonium ion with phenol. Remember, when a diazonium ion reacts, this is the kind of product that you should get. The triple bond of the diazonium becomes a double bond. Remember that the OH will be as far away from the diazonium group as possible. So this is what we call a para substitution. The last question says hydrated calcium benzoate is used as a preservative in soft drinks. It has this formula, so this is hydrated calcium benzoate. 2.6 grams of this salt was dissolved in deionized water. Excess lead 2 nitrate was added, forming a precipitate of lead 2 benzoate. This precipitate was removed and dried, and the mass of the final solid was 3.89 grams. Calculate the molar mass of hydrated calcium benzoate and hence deduce the value of X. So we have information about what? We have information about the mass of lead benzoate and the mass of the original hydrated calcium benzoate. So he's telling me that 2.6 grams of the hydrated calcium benzoate gave 3.89 grams of the lead benzoate. So I can get the MR of the lead benzoate first in order to get the number of moles of lead benzoate. So number of moles of lead benzoate is mass over molecular mass. I calculated the molecular mass. It came out 449.2. So this gives me number of moles of lead benzoate. And then 1 mole of this gives 1 mole of that. So this is the same as the number of moles of calcium benzoate. So I can use that to get the MR of calcium benzoate. The MR is mass over number of moles. This gives me an MR of hydrated calcium benzoate of 300.2. And I should be able to calculate the MR of the anhydrous. So the MR of the anhydrous is the calcium plus the C6H5COO twice. This comes out to be 282.1. And that means the difference between them is the MR of the water part of the XH2O. The H2O alone is 18. So if the XH2O is 18.1, that means X is 1. So we got the value for X. Okay, and that was the last question in the paper. I hope this was not too long for you. Please study whatever you find is difficult, and good luck in your exams. Thank you for listening.